Hello, welcome to Third International Congress on Human-Computer Interaction Optimization and Robotic Application. Due to COVID-19, we are holding our symposium virtually. I hope this epidemic will end as soon as possible. Okay, let's start the session. First paper is belong to Mr. Rashid Dağlı. Rashid Dağlı, are you ready for your presentation?
Rashid, you're muted.
Okay.
Oh, sorry for that. Can you hear me?
Yes.
Yes.
I'll go on to share my screen.
Okay, you can start your presentation.
Thanks. I hope you can see my screen and I'm audible.
Yes, we can see your screen. Go ahead.
Thanks. Thanks for confirming that. Hi, I'm Rishit, and I'll start off by saying that I'm thankful to all of my co-authors for this paper. And in the next 15 minutes or so, I'll be talking about our paper, job descriptions, keyword extraction using attention-based deep learning models with BERT. And I'll try to explain this in an intuitive way. I'll try to explain that paper in a...
Sorry, you have 10 minutes, please, okay?
Okay, I'll try to explain our paper in a rather intuitive way. In this paper, we focus on creating a keywords extractor, especially for a given job description or a job-related text corpus for a better search engine optimization. And we aim to make this as easy as possible and be this usable for multiple use cases where keyword extraction is an important thing. And we also validate our results and investigate the modeling power of both for the task of keyword extraction from job descriptions in this paper. I'll first off go on by talking about the problem which our paper aims to solve. So explaining this in a rather intuitive way, I'll start off by saying, I want you to think about a sentence. Harry reacts to this in a rather awkward manner. So in this sentence, let's say if you are given the task of extracting keywords from this, there are multiple ways of rewriting this text for summarization or for finding the keywords from this. You can, so the keyword highlighted over here, the word highlighted over here, react, is probably not important in its exact form. You might want to rewrite this for summarization using the base lemma of the word react. Maybe you can make it reacted or something like that. And you'd probably also skip this word while extracting keywords. And I want to talk about another example, pretty much related to the kind of problems we validated the algorithms we present our paper on. And let's see what this about the sentence. Applicants should be well versed with React. Here, if you see, well, the word React cannot be skipped. The word React should not be skipped. It means something else. It means a particular text stack in a job description. And it should also not be modified. You cannot take the base lemma of the word React. So the problem we face over here is that our machine learning models are not able to take the context or semantic of the sentence. And several neural models comprise of pre-trained word as task agnostic embedding layer, and the neural architecture or the downstream model with all of that is usually.
Someone started sharing the screen. and the presentation went off.
Oh, yeah. I'll probably reshare my screen then.
Yeah, please go ahead. Maybe the host can. Okay.
You can probably see my screen again, right? So, as I was saying,
Right.
several neural models have been proposed in the past, which use a task agnostic embedding layer and then use a downstream model which has been optimized for the particular task. So, just that our downstream neural architecture is optimized for the particular task. In this case, it could well be job descriptions and how to extract keywords from that. So such models improvements, either measured through the correctness or the F1 score, has pretty much arrived to a bottleneck. And the task agnostic embedding layers are often linear and provide context independent characteristics. It cannot identify the context. It cannot, while making embeddings, it cannot identify the context in which the sentence is used, in which the token or the word is used in the sentence. And these embedding layers cannot capture dependencies or context-based semantics in a particular sentence. This is some of the major flaws with the previous work in this area. And let me now talk about the system design and what our paper proposes. So as we talked a bit about this, traditional embedding models often give single context independent representation for each token. So for the same token, used in different contexts or in different sentences, you would have the same representation for it, though the context in which it is used is quite different. And this can often lead us, or most of the time leads us to losing the correct sense of the token, or the correct sense in which it is used. And it is highly inadequate to capture the dependencies of semantics in a particular sentence. So we build on top of the BOAT model and modify the existing BOAT model to use it as an embedding layer. And we use 3 embedding layers specifically to preserve the context. The token embedding, the position embedding layer, and the segment embedding layer. So this is how our model architecture looks like at a high level. And let's talk more about the first aspect of the model, where we use BOAT as an embedding layer. The modern architecture of both component is based on transformer encoder of multiple layers, and such a mechanism being bidirectional eliminates the limitations of self-attention, which can just integrate a one-side context, maybe a right-side context or a left-side context. But we build on top of both, which allows us to use a bidirectional context, create the representation for a particular token in a sentence using the data from the whole sentence. So we use both as an embedding layer, which uses transformers and eschews recurrence. So it is based solely on attention mechanisms, and compared to the traditional layers that often just represent context-independent representations for every single token, we now use a complete sentence as the data to identify embeddings or represent a particular token in the sentence. So this allows it to learn relations as contextuals between text, subwords, or words. And on top of this, we also investigate the fine-tuning impact of the performance of the fine-tuning impact of both on the final performance. So precisely, we implement both to figure the contextualized representations at the token level and keeping the board component parameters fixed at the phase of training, and compare those with the models with fine-tuning board and without fine-tuning board. And finally, our end goal with this is to use the contextualized representations at the token level for the downstream task, which is us validating if if our model works well on job descriptions, identifying keywords from job descriptions. So being a bit specific about how we use BOAT as an embedding layer, as I mentioned, this time we use the data as a complete sentence. So instead of just the token, now we have a token sequence which we put in. the complete sentence, and the board component calculates contextualized representation. So here we regard HL-largely contextualized input tokens for at the contextualized representations at the token level, and utilize these for the downstream task. And so so this just shows a quick example, a quick screenshot of the embeddings created with board, where I can, and these are also made public, so you can try this out. This just shows of the embeddings created with the model built on top of board, and how it is able to identify semantically close tokens. Let's now, I'll also talk a bit about the downstream model, which is essentially just a model we use on top of the contextualized representations given to us by board. And we use simple DNN models for the downstream task of keyword extraction. With that, I come to the part where we talk about the results of our paper. And we start off by using both base and case model, where the number of transformer layers we use is 32 and the hidden size dimension is 1024. And I want to talk about this particular point. I want to talk about this particular point due to the comparisons we make between fine-tuning both and the different variants of both. So we also compare our model with other variants of both, uh, and of course compare it with the baseline TF-IDF models. We specifically compare both with three other variants, both GRU, both CRF, and ALBOD, observing the FN scores on the development set for the final output. We observed that no significant performance increases were shown with any of these models except ALBOD, which performed significantly lower than using all of these other models as embedding layers. However, we also observed that using both base and case is quite robust, and it is quite robust to overfitting on comparing with other variants. We also, in this paper, we also investigate the modeling power of board and observe the impact of fine-tuning board and the impact of fine-tuning board on the final performance. So we use board to calculate the token level representations while keeping other parameters of the board component constant while training to make comparisons between the impact of fine-tuning. We observed that the pre-trained board representation was far from the satisfactory results, and we observed almost 25 to 35% improvement across all the variants of both GRU, both CRF, and the both base and case model, and approximately 27% increase, 27% increase in performance with our best performing model, the board base and case model. This also shows the superiority of the board embedding layers in aspect-based keywords, and shows the modeling power of board across different tasks. We further also validated our results in this paper and tested it out on real life job descriptions through a built API around this model. And with that, I pretty much come to the end of this paper. And this research was supported with cloud TPUs from Google's TensorFlow Research Cloud. And many thanks to them. I also come to the end of my presentation, and I'm out of time. So I'll leave it up to the organizers if you want to take any questions or if there are any questions.
Okay, thank you for your presentation. Dear participants, do you have any question about this article? Okay, thank you again. I wish you success. Next paper belongs to dear Hassan Perez. Dear Hassan Perez, are you ready for the presentation?
Good day.
Okay, you can share your screen.
Yeah, let me share my screen.
Share screen button is bottom of the. Okay.
Yes. Okay, so how much time do I have?
Yes. You have 10 minutes, please.
10 minutes. Okay.
At most.
Good day. My name is Hassan Perez, and I will talk to you about the design and implementation of a cognitive ability virtual reality training tool. This project was made for the Masters in Process Design and Management for the Faculty of Engineering of Universidad de La Sabana. So virtual reality has very high immersion and presence. It has been used not just for games, but also to train either through simulation or with the use of serious games. It is a very efficient tool for training and possibly also very cost effective. With that in mind, we set out to create a training tool that improves the cognitive abilities of working adults. Cognitive abilities in the form of executive functions. Executive functions are what we use when we are conscious, when we are concentrated in our tasks. Like, for example, listening to someone and understanding what they're saying. And we set out to design this training tool with a strong design and testing before the actual implementation. So for methodology, we set out to develop a VR training tool. So where to start? We went to the literature and researched about the video game development software engineering cycle, or GDSC. You can see a schematic of the GDSC in the screen. And we also researched about focus games to train cognitive abilities that were already out there. So how to train cognitive skills? According to the literature, it needs to be a difficult activity. It needs to be random, that is, to not have a perceived pattern. It needs to have a time limit as to push the person to do the tasks, and to give feedback on right and wrong actions. We turned these characteristics into playability elements. So we first made a paper prototype that include these elements. We then created a game that is about following instructions, and the instructions are built depending on the elements on the game board. So what is the game board consist of? Since we are aiming to train working adults, we need to use elements that are familiar to these people. So we settled on construction tools like hammers and pliers. And we also used simple containers to place the tools in, and different distinct colors for the tools and the containers. So what is this game about? It's a game about following instructions to take a tool and place it inside a container. The instruction may change, mentioning the tool name or the function of the tool and the color. And it can also change, mentioning the container name or the container material and the color. And the further you progress on the game, the more possible variability in the instruction. With these rules figured out, we wrote out the game design document. After that, we decided to do some real world tests to see if the rules make sense and are motivating for the players. We made two variations of the rules. The first variation is what I described you, different tools with different colors and material characteristics, along with different materials. The second variation was just one tool for a job each, combined with a color palette, along with different containers. That way the player would take the tool and combine it with a color. The graphic on the right shows the results of these tests. We made these tests mainly to figure out the times that people would take to follow the instructions, but also we wanted to test how easy or motivating the game would be. Apart from taking the times, we made a simple interview to all the participants. And in general, people prefer the first variation. It appears that it's more fun and motivating to choose from many different items, many different tools. Now, to the actual implementation, VR development requires three components: a game engine, a virtual reality software development kit, and the integrated development environment. For the game engine, we went with Unity version 2019.4. For the SDK, we used Unity XR with the XR Interaction Manager package. And the IDE would be Visual Studio Code. We made this project for the Oculus Rift head-mounted display. So how to do this? First, we set out the scene. We took different free assets from the Unity Asset Store and arranged them in a way that gave the player the feeling that they're inside a warehouse. After that, we set out the VR rig using the Unity XR libraries. And then we could set out and implement the rules of the game. This flow diagram shows the rules for the main game. You are given an instruction. You take a tool, put it inside a container, and the game tells you if you follow the instruction right or wrong, and continues until you complete all the objectives or run out of time. And this is the UML diagram of the implementation. We use the actor model with an entity component well, so here you can see the containers and tools hold information for those items. The instruction builder is kind of like the central class that takes the information on the tools and the containers and shows it on the screen on the user interface. And there are several other classes that handle level transition, and the timer, and the end game state. So the results is a VR training tool that is about following instructions. You take a tool, put it inside a container, and it gives you a visual and audio feedback about if you did it right or wrong, and you have a time limit. These screenshots are shown in Spanish because this tool was developed in Latin America. So in conclusion, by researching the literature, we made a virtual reality training tool focused on the improvement of the cognitive abilities of working adults. We followed the video game software engineering cycle, discovered how to train cognitive abilities, extracted those characteristics for those trainings, and turned them into gameplay elements. Then we set out to make a paper prototype. We implemented for a VR head-mounted display. We set up the virtual scene, we set up the VR rig, and then we programmed in the interactivity and the rules. After that, we went through usability tests and modified the training tool accordingly. And at this point, further research is needed to determine the training effectiveness in working adults. These are all the references, and thank you for listening. I don't know if you have any questions. Do you have time for questions?
Thank you very much for your presentation. Dear participant, do you have any question about this article? Okay, thank you again. I wish you success.
Thank you.
Next article belongs to George Krastev. Dear George Krastev, are you ready? Dear George Krastev, maybe may not online. Dear Salah Aboud, are you ready for your presentation?
Yes, I am ready.
Okay, you can start your presentation.
First, I'm so sorry. I think I have some problem in my camera, so I'm sorry.
Okay.
Dear
It's
Chair
not problem.
and keynote speaker, good afternoon. The presenter is Muhammad Salah, paper ID 135. The analysis of teletraffic and handover performance in cellular system. The outline: introduction, method, result, discussion, conclusion, and future work. Under simplified consumers' mobility in a handheld cellular network environment has been formulated. Mathematically, a computer simulation was built on the basis. This mobility model is used to investigate the distribution of cell residence time in mobile environment, described by cell size and parameters for mobility. The handover phase or handover is in private is every cellular ratio device as far as the end consumer is concerned. In this figure, a call may be described as one has only been initiated in the cell, or one that has been handed over to neighboring cell. The life of mobile phone began when it began serving a call and ends when it leaves the unit. Handoff time expanded by the smartphone as it had advanced one handover. Our mission is to create a mobile simulation. Sorry.
Okay, you can continue.
Okay. Our mission is to create a mobile simulation focused on a parameter like that following structure, traffic, mobility, handover, and propagation. Then collect and quantify the telemetry from the cellular and handover. This lets us build a mathematical simulation model of a boundary condition for the project. The models is most often used to distribute a cell residence in the system. The method for this slide: to get around the difficult unadjusted cell is situated by a cell whose value corresponds to the previous. In other words, In other words, it follows an alternative formulation that depicts mobile trajectory as a sign cell and resolve the issue at the stage. Finally, from time to time, a memorial re-entering and re-entering mobile into the original initial cell in this figure. As many as 7 hexagons are calculated in the Monte Carlo simulation process. Construction regular omnidirectional antenna in the center of the hexagonal array produce a complete grid. In order to create the network topology in MATLAB, 2 elements must be taken into account. The first innovation is base station assigned. The second is hexagon cell, 6 cells away from the original hexagon we built are in the depth of the first one we started. The gap between the base station is essential, whereas the cell reduce has no bearing on how far apart they have located, like D or equal or multi-square 3. On the other side, the mobile station is simulated randomly in design. Before started the simulation, the consumer will be required to input the number of cell station needs to the tail traffic network. Math equation were implemented to the established location and coordination in the X and Y axis. For our result, and we have, or as we have set the radius of a hexagon cell to 5. The cell is began to generated from the center to of topology. The 7 hexagon cells are generated. Hello? Are you hearing me, please?
Continue, Mohammed.
Continue, please.
This allows for equal transmission power and stable interference coordination between each core or cell. Plus, we assign the main station at random coordinate by applying the Monte Carlo method. This is an advantage of Monte Carlo. Seen in figure 3 to 5, when the user insert the value of number of mobile station, for example, MS equal 3, the user has to define the simulation time, sim time, which we insert 3 seconds of simulation time before proceeding. Later, the simulation will randomly assign the main station into random coordination. In this section, we can to show the call traffic for 5 calls for the teletraffic. This graph determines how many calls have been in idle, active, blocked, or stop status in the y-axis. It also shows the length of the call on the x-axis. We define the number of calls equal 5. Within simulation time equal 150. Description of graph, the first one, the call is active in progress for 50 seconds. Eventually, the call ended for the next 100 seconds. The second, the call is active in progress for 90 seconds and eventually ended for the next 60 seconds. The call is active for 150 seconds. The last one, the call is blocked for 120 seconds, end to end, between active and the next 20 seconds. In this slide, from the block and the main station 2 moves towards base station 1, the value of SIR increase, and main station 2 obtained highest peak at equal 18. When the location of main station 2 is very close to the base station, co-channel SIR value equal around 258. However, as main station 2 goes on towards base station 2, the value of SIR seems to decrease because the helpful signal power was decreasing. Another peak of SIR value achieved when T equal 57, but the co-channel SIR is not high compared to the earlier B connection because the location of main station 2 is not close to base station 2. And the interface signal from base station 1 and base station 7 also affect the value of the ratio. The movement of main station 1 or MS1 is smaller as compared to the main station 2. The value of the SIR is more stable for MS1 due to its movement. However, as main station 1 leaving base station 6 and move towards of base station 7, the value of the SIR is decreasing, and it's begin to decrease at equal 108, while the value of the SIR is 0.155. When it start to move from the base station 6 cell, the value of SIR seem to decrease as low as 0.8 and begin to increase as it moves towards for the base station 7. It may be caused by the higher useful signal power served by base station 7 as compared to interface from base station 6 to base station 1. The value of co-channel SIR for main station 1 increased until 7.3 when the simulation and the call is blocked for 120 seconds and being active in the next 20 seconds. In this slide, we can explain the first plot and second plot of this figure. Show the handover process for main station 1 from base station 1 to base station 2. At simulation time around 93, the main station 1 has been attached to base station 2 from base station 1 based on the highest power transmission received while in mobile, as mentioned in section C. This has been supported by the distance of the main station 1, which is near to the base station 2, and it is, has the most suitable RSSI value recorded during the simulation. Our conclusion: the simulation project has enabled us to learn to use MATLAB by conducting math time-driven event simulation and event-driven calculation in Monte Carlo. It has a Monte Carlo simulator used to build these 5 models. called propagation, interference, traction, and mobility together make up the intervention traffic simulation. Our vision or future work, the upcoming experiment and research is that several plants are used and more than double the cells and nodes that were used in the experiment. They make a comparison to get novelty results. Thank you for listening. Any question, please?
Thank you very much for your presentation.
Thank you.
Are there any questions about this article? Dear participants, you can ask Mr. Mohammed. Okay, no question. I wish you success.
Thank you again.
Thank you.
Thank
Thank
you
you
very much.
again. Okay,
Thank you, Jeff. Goodbye.
goodbye. The next paper belongs to Takiro. Dear Takiro, are you ready? Dear Takiro. Okay. Dear George Krastev. Dear George Krastev, can you hear me? Okay, next paper. Dear Elmash Hadani, are you ready for presentation? Elmash Hadani. Okay. Dear Jabir Mamadov. Dear Jabir Mamadov. Okay. Not online. Is there any participant with a paper in this session? Waiting. Okay. Dear George Krastev, are you online? Dear Takirov, are you online? Elmash Hadani, are you online? Dear Jabir Mamadov, are you online? Okay. I want to end the session. Thank you very much for attending. I wish you success. See you in other symposium we organize. I wish you continued success in your career. Okay. See you other session. Have a nice day.